All right, so here we are for chapter 7. We're going to be talking about confidence intervals. The main idea of a confidence interval is, well, what we see here, that we can form a plausible range of values for the true population, either proportion or mean. Sometimes we just refer to that choice as just a parameter, so whichever one you want it to be. Parameter could mean mean or proportion, but here, for this sake, we're just specifying which one of the two we're going to be looking at. And then, of course, the key idea here that makes this interesting is it's based only on sample data, which is a pretty neat idea that we can just simply use a sample and infer or estimate or form a basis for what the population could be, even though we only have a sample of that population. Now, as you can kind of see through here, we're going to be dealing with two different formulas, and those formulas are for, the two different types, whether it's proportion or mean, and those are split into our two sections, 7.1 and 7.2. Now, the formulas you can see are pretty small, and there is a way to kind of piece them together to where you don't need to memorize them on the formula sheet that you have. But what you need to remember is that when we are dealing with proportions, it's definitely going to use a z-value. And when we're dealing with means, it's definitely going to be a t-value. Now, the other thing about a confidence interval is it's kind of like the normal distribution, or because it's based on the normal distribution in a way, it's going to be still centered at 0 and be symmetric. So, in other words, when you look at these formulas, you can see that there's a what we call point estimate, and I'm kind of down here just generalizing that for point estimate, plus or minus some margin of error. So this entire right-hand side gets referred to as the margin of error. Now, the other thing about this entire margin of error is it's split between your critical z or t value and your what we call standard error. So those two things are forming your margin of error. So ultimately, it's the point estimate plus or minus some margin of error. And so it's going to be symmetric around that point estimate because you're subtracting some amount and you're adding the same amount to it. So symmetric around the point estimate, and you're adding or subtracting your margin of error. Now, speaking of symmetric and being kind of centered, let's look at our first early question that kind of dives into this idea. This is a very oddly worded question, but a very easy question based on what we know from chapter 6. So the idea is, and I even downloaded an external app to try to draw better lines because the mouse speed was too quick. So let's see how this goes. Good enough. Remember that the normal distribution is centered around 0. And so what this question is saying, goodness, there it is saying there's some values here. And we want to know where there's 82% in the middle. And so what on earth is this saying up here? Here we go. Well, it's saying if there is 82% in the middle, then what's on the outside? The complement to that is 18%. And because we're symmetric, there's going to be 9% to the left and 9% to the right. So why is it called z alpha divided by 2? Because, well, what we're saying is if I was able to capture 82% or be right 82% of the time, or to be 82% confident, then I'm 18% unsure. Alpha essentially stands for the error you're willing to give, so to speak. Like the error you're willing to let happen through the statistical process. And so if I want to be right 82% of the time, I must be willing to give up 18%. Alpha would represent that 18%, the chance that I'm wrong if I say something conclusive. Now from there, we split that alpha into two sides. 18 is split in the middle because we're centering this 82%. Kind of like the empirical rule, plus or minus some amount gave you a left-hand side and a right-hand side from the middle, and there was some left over on the outside and some left over on the outside, and it was symmetric. And so the way we answer this question is actually not too bad. We're just going to say, okay, then the easiest way to answer this answer is find where 9% area is on the z table. Now that's why we're looking for the critical value of z alpha divided by 2. It's literally saying find the critical value where the z value has 9% area to the left, right? There's alpha, 18, divided by 2 is 0.9. So find the value where there's only 9% to the left or only 9% to the right, which would actually be, if you think about it, 91% total area. That's a big misconception, is that people start looking at the 82% confidence level and they look for where there's 82 in the middle of the table. But remember that 82, or rather the table is saying, and let me pull up the table real quick. So remember that this table is always telling you your value, your z value, all the way to the left. And so if you go looking for 82% in the middle of this table, which looks like the closest I can get is right there, that is not going to be the correct z value, because take a look at this chart again. This is not 82% of the area all the way down. It's actually either 9% all the way to the left, or cumulatively, right? If there's 9% here, what's left over? 91%. So be careful, which is again why we say just find the opposite, right? If I have 82, I lost 18. I'm willing to lose 18 or be wrong 18% of the time. Cut that in half and just find where there's 9% area on the left. It's equivalent to finding the positive version over here with 91%. And maybe we'll even show that. So anyways, let's find our 9%. Closest I can get to 9% is right here, and that's negative 1.34. All right, and so maybe we'll just snip this into the notes. And we'll have to make that a little bit small, but we can zoom back in on that later if you need to. But that comes from, let's insert a text box here. Z equals negative 1.3. I know that's small font again, but and then 4 gets tagged on. And so also the idea is it's either the plus or the minus, right? Let's look at positive 1.34 and see what it gives us. If I look at positive 1.34, hey, look at that. There's my 91% instead, like I was referring to. So either way we get 1.34, and so therefore we now know the critical value that we needed. And maybe we'll just even, increase the font size of that since that's our answer, and then we'll move on. Oh, now I made the scrolling speed too small, so it feels like I'm moving the mouse over a whole century just to get that. All right. There we go. That looks better. Now, also, your homework is just going to want the positive answer. I'll go ahead and say that, but either works. And really, it's that both are there. There is the negative 1.34 and the positive 1.34, but the value, regardless of sign, because really, the plus or minus is already in the formula. Just what is that value would be just the 1.34. Okay. Now, also, of course, there is a way to do this in StatCrunch. So maybe let's do one more example and see how that shows up. So this one, they wanted 91%. So that means there's 9% left over. Oh, look, there's where I got it from. That means there's 9% left over, which means there's 4.5% on either side. So let's show you the two ways of going through that. I know I said it all out loud, but 9% left over. And so that means there must be 4.5%. And careful how you write that. It should be 0.045. Area to the left. And there's my negative 1.695, which would round to negative 1.7. And I'm going to give the positive value like I warned about. Okay, but let's go back to StatCrunch real quick. Hey, look, you could select that you want area between, and you could say I want 91%. And there it is, the negative and the positive all in one step with no effort. So there you go. You can just use, that was calculators in the stat menu, the normal table that we'd used all the time in chapter 6. So that's showing up and still being useful again. This next question I'm going to let you go through on your own. It's actually super, super simple. So is this one. It's just really different ways of writing the same prompt. And now let's go through this question right here. Just one example where we go through the whole process without a calculator, and then we go through using StatCrunch. And let me just gather my windows here. All right, so I've gone ahead and copied in that question, and then there's our formula. And so the first thing they ask online is find the best point estimate. Well, a point estimate is simply that first thing in the confidence level. So really, I'm looking for what is that p hat. And so that p hat is going to be, well, my successes, or in other words, the event I'm looking for, which is find out who feels vulnerable to identity theft. So there we go. I found 562 that said yes, they do, out of 923. And really, we just need to work that out and get a nice decimal for it. And let me pull out a calculator real quick to do that. And I think I saw real quick in the homework that they wanted this to 3 places. So 562 divided by 923, I'm getting 0.6088, which would be 0.609. All right, there's part 1, 0.609. Up next, they want the margin of error. Now that one's going to take a little bit more, but the margin of error is, again, well, you know what, let me write it out here with our math print, because I can type faster than I can write with the mouse today. So first, I'm just going to write that it's some sort of z-value times, and then I've got that square root, I've got that fraction, and let me zoom in here. Oops. But let's start filling things in now. So the margin of error is both of these things put together. And so first I need to figure out what my p-hat is. Well, I actually already figured that out. It's 0.609. P-hat's complement, 1 minus that, is going to be 0.391, because those two add up to 100. Or again, I just subtracted from 1. And I also already have the sample size. I already used it. It's the 923. And so now the question is, what is that z-value? And hopefully we can use a different font color here. But I already know, I think it's going to be 2.576. But let's see if I'm right, and let's see where I got that from. If I look at the bottom of this t-table for 99% confidence, whoops, did I did 576? Awesome, I did. So I still remember it. On the bottom of this t-table, you can even see there's a confidence level chart. And so all I had to do there was literally just look at the chart and use the bottom value when I was done. And so let's draw that or underline that in green to show, hey, that's where we got it from. Gosh. This mouse is very sensitive. All right. So there we go. That's where we got the 2.576, and so we're done with that part now. And let me get off the drawing tool and just say that there's my margin of error. Oops, but I don't want to write that in green. My margin of error is that. And I'll once again need to figure out what that is, and I'll type that into a calculator and write that down. All right, so after typing that in, I ended up getting 0.0413, and let me just again write that that's where that's from. And let's type that in, 0.041. Wouldn't round up, so there's my margin of error. Awesome. Next, they want you to construct the interval, and that shouldn't be too bad because it's literally, let me zoom out a little bit, it's literally just my point estimate minus this value, my point estimate plus this value. So give me a minute while I do some mental math. I think it would end up being that because of the way I'm subtracting, and then that would be 0.650. Pretty sure. Great. I can do by mental subtraction. Now the one last thing we haven't done yet is we haven't figured out how do you conclude these things, and so the way we do that is we say that we're 99% confident that the interval from my lower bound to my upper bound contains the true value. And that phrasing, although it sounds a little bit different, is exactly what we wrote down here. It's that if I've formed a confidence interval, then I have formed a plausible range, so everything from the lower bound to the upper bound, for the true population proportion. And the only thing there is we add this one little additional statement that we must say that we are 99% confident that blah blah blah. I found the true value within the range. Now let's just look at the other ones and see why they're not correct. We never say the word chance. We always have to say we're 99% confident. So far, B and C are in the running, but B was already correct. And let's just check it just to be sure. Oops. Let's go back and look at the others, though. One has 99% confidence that the sample proportion is equal to the population proportion. That answer should sound like nonsense when you reread this statement. What are we trying to do? We're just trying to say, in my range of values is the true population proportion there. And I'll never know for sure, but I can be blah percent confident that it's there. Not that it's equal to some value, but that I caught it within some range. So definitely not C, because it's saying I got the exact value right, essentially, when I found this value. No, that's not going to be the case. But because I'm using that value and a standard deviation to form, an error around it of the likely possible values, then I can form this interval. So anyways, it's not precise single value. It's just saying I think somewhere between here the real value is there, and I don't actually know what the real value is with certainty. All right, last one, 99% blah, 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 but it doesn't say 99% confident that, and really you can stop reading from there. So at that point, there's really only one more thing to do here, which is do another one of these problems, and essentially just say, well, let's go ahead and see how to do this with StatCrunch. And actually, I think I want to redo the one we just did. And we'll just redo this question, and we'll do this using StatCrunch only. So let's see how to do that. So what we can do is we can go to Stat, and we can go to Proportion Stats for one sample, and I only have the summary there. And you can see we get these questions, what were the number of successes, and you can see from that prompting, this time it's 582, the observations is 906, and we want a confidence level with 90% this time, and you might as well say, show me the critical value. And actually, you're going to need to say, show me the critical value. So that's a really simple menu. Again, we went to, where did we go? We went to Stat, Proportion Stats, one sample, and with summary, because we didn't have like all the data, we were just told the yeses and nos out of how many. All right, make sure you click the show critical value. I'll show you why that matters. But first, you can see there's my sample proportion, my 0.642. So there's my first answer. Way easier, way less calculator work. Next, the margin of error. Now, you're still going to have to use a calculator here, but the margin of error is your standard error times your critical z. So when you take those two numbers and you multiply them, just trust me, that's your margin of error. And from there, at the end, they give you the lower limit and the upper limit. So, you have one multiplication to do there, and that's what's my standard error times critical value, because that's your margin of error entirely. You can't just type that standard error in that box. It won't be correct. Okay, so great. We saw how to do that. Now let's go and look at, say, best score. Now let's go ahead and I think I want to look at, this question here. So it says there were 512 human resource officers and 45.5 said that body piercings and tattoos were red flags. So the first question is, and really, again, in this class, you've probably realized it by now, but really we're just professional window shufflers here. We've got our data and we got to figure out how to type it in where we need it. Okay, so come on. All right, so we sampled 512, and I need to figure out essentially, okay, they already found my point estimate for me, so to speak, but where did they get that from? Well, take your total and multiply it by that decimal, and we now figure out that it's essentially 233 people that said yes. 233 HR reps said yes, tattoos are red flags. All right, so just a little bit of like decomposing. Where does that estimate come from? All right, from there, believe it or not, it doesn't seem like we have enough to form a whole interval, but we do. We can press get more help in StatCrunch. I think I already got a window open somewhere. Maybe I don't. Like I said, professional window shufflers. All right, let's find our interval. So proportion stats with summary. Number of successes I just figured out was 233 out of 512. I'm doing a confidence interval, and they wanted 99% confidence. Show my critical value. And right there, I already have my lower limit and upper limit, so 0.398 and 0.512. 0.398, whoops, 0.398, 0.512. All right, this time we get a fun question. Repeat the problem, but just do 80% confidence instead. I like that because it really shows what that confidence level does. So we still have 233. We still have 512 total. And now we only need to be 80% confidence. So what does that do? Now we get between 0.42 or 0.427 and 0.483. 0.427 and 0.483. All right. And then it just says compare the intervals. Now, let's say it this way. You want to think about this like almost a dartboard and a target. And you want to be able to kind of ask yourself, am I sure I could hit one of those like concentric circles on the dartboard? And the answer, hopefully, for most of us would be that the wider out we go in those circles, the more we're sure we'd hit the dartboard anywhere, right? Like maybe not all of us are getting a bullseye, but a lot of us can probably get a dart on the board. And so that's a weird way of saying it, but I hope it kind of shows what's going on here with these confidence levels. I can be pretty sure I can hit the board, but it's going to have to be a wide target in order for me to be sure I'm going to hit the board, or almost sure, right? There's always a chance that we just miss and hit the wall. But if I don't need to be as confident, or if I say, honestly, I think maybe I could, but I'm not sure, it's probably because that target's narrower, if you think about it like that. So maybe I think the first way of saying it sticks a little better, but the more confident you are that you'll hit the true value or hit anywhere on the dartboard, it's probably because you have a bigger target that you can hit within. Or in other words, think about it like maybe a giant fishing net. If you drop a very, let's see here, a very small net in the water and try to catch fish, and you just pull it along. If the net's small, you might not catch that much. You might not be sure you catch anything, right? So the smaller your net, the smaller the window you have to look through, the less likely you can be sure that you actually got the true value. And if you really want to be sure that you're going to at least catch one fish, then you need a very wide net. So that's what we're doing. We're fishing for the true value. We're making a good educated guess based on the normal distribution in our sample size and in that big wacky formula. And, again, we haven't got into the total theory of where that comes from, but I almost want to say in Stat 1, your first stat class, you don't need to know the theory, but it's nice to have. But essentially, the normal distribution is letting us create this net out of just one little sample. Really powerful idea. Anywho, if you want to be sure that you're going to truly catch the population value, if you want to be 99% sure, then you're just going to have a wider interval because you need to make sure it's wide enough to capture the likelihood of what the true value could possibly be. Okay, comparing the intervals, let's see here. A confidence interval must be wider in order to be more confident it captures the true value. Hopefully just all my rambling said that for you. But whoops, this is the wrong phrasing. The 80% interval is wider. No, it's not. The 99% interval is wider because it must be wider in order to be more confident, in order to be sure that you got the true value. And honestly, I this is the first time I've said that fishing analogy, but I kind of like it because that's the idea is when you drop that net in the water and you're just pulling it behind a boat, you won't see what it is until you pull it up or have the net. In other words, we never actually know if we captured the true population value because, let's say it this way, if you knew the true population value, there'd be no reason to take a sample and form a confidence interval. So it's kind of like a confidence interval is your first exploration into what could a value be for data. And, answers to questions like, honestly, today, like popular research questions, I know we don't want to hear it, but asking, who uses ChatGPT or what proportion of students are using ChatGPT, honestly, that's a question that doesn't have, at this point, I would say, a solidified population parameter to it. We don't know what the answer is for sure, and this would be a great use for confidence intervals. There's this brand new thing, AI and ChatGPT, and I'm not trying to pander and be that person and bring it up, but really it is relevant that that's a area of research and a tool that's being used, and it's really uncertain to what degree it's being used out there in academia. I mean, I'm sure everyone just assumes we're all using it, but to put a precise number on it, to have a certain degree of confidence about what the true value could be, since it's this brand new kind of can of worms that's opening, really, that's where you would use a confidence interval in real life, which would be kind of interesting to do, but we don't have time to do it here in this class. But maybe that's what we do as, if we taught a second stat class, what your final exam project could be is go out and research and form a confidence interval about it. Anywho, I've got one more question here, which is kind of odd in its phrasing, but the idea is, let me see here. We now want to say, well, how many people should I form to get a confidence interval? And it turns out that you can essentially take this margin of error formula and rearrange it, or in other words, you can just use StatCrunch to get your formula for how many people should you answer if you want to be confident about getting a certain value or a certain margin of error. Okay. Actually, sorry, there is one more thing to say there. So, in total, then, here's what we're really saying. There's two things, and maybe we should just add in a second slide here. There's two things that control the width of an interval. And those two things are sample size and confidence level. Now, the thing that we should maybe say about them is, really with sample size, it's always better to have a larger sample, a larger, truly randomized sample, because one thing to say, just to really call back to chapter 1, is if you sample poorly, if you sample everyone that walks into the Ocala Paddock Mall, then although you did take a random sample, depending on if you're trying to gather like general mall statistics, really you just sampled from one mall and on probably one day of the week, and you called it a day. Right? If you really wanted to sample all malls, then you would need to get a sample of all malls and go out there on multiple days. And so it's always better to have a truly randomized sample, and it needs to be a good random sample that generalizes properly. Like I said, right, if I want all mall goers and I only go to the Paddock Mall, I'm really not able to talk about all mall goers because I've narrowed my sample down to one mall in Central Florida. So randomizing is hard, and so again, it's always better to have a large, truly randomized sample that meets my goals of who I'm trying to study, but it could be expensive. Right? Because if you truly wanted to survey, you'd rather have to pay for database resources, pay multiple people to go out there and stand. It would take your time to do that and gather all that data, or even like travel across the country to go to different malls. So sometimes we just don't have literally the physical means to do it. So it's nice to have a bigger sample, but you might not have the budget or constraint or time to do it. Now, confidence level is your choice as well, but as we talked about, if we want to be more confident, we may form an interval that is so wide it can't be conclusive. Right? In other words, if we were just to say in general, hey, what do you think someone's going to get in this statistics class? If I just said, oh, I think most people will get somewhere from a 0 to 100, that I haven't said anything meaningful about how likely I think someone is to pass, right? I'm literally saying it could be anything. And so same thing if you're trying to like do who's going to win the election or something, or who's likely to vote for this person, and you end up with an interval that goes anywhere from 0.4 to 0.6, then you've essentially said it could be the minority and it could be the majority, right? I'm gone from less than half to over half all in one interval. And so if it's too wide, that can lead to like inconclusive things. But there is a other side. If you have a narrow interval, but you can only be 20% confident in it, that's still not good either. So there's a balancing there. And honestly, I think the biggest thing to take away from this kind of discussion is confidence level is usually never mentioned in like news headlines, but it's super important that you mention it, because if we say this person's, polling and they're, currently slated to win, maybe that was based on an interval that was only at 60% confidence level. So they told you, hey, the data shows that they're in the majority for the vote, but maybe if we slid that confidence level to 80 or 90%, we would have creeped into the minority side and gotten some less than 0.5s in the interval. And after all, anything in the interval could be fair game. So that's a lot to digest there and say, but really it's those two things are in your control, and they both have, cost and benefits to them. So, anywho, by doing that, we can essentially say, well, what if I want to be, right? And here's the idea. What if I want to be within 8 percentage points? So if I want that, then maybe there's a way that I can just figure out my minimum sample size needed. And it turns out there is. So all that lead up, again, to a really quick question, but hopefully we just kind of understand some of the theory. So we're still in proportion stats. We're going to one sample, but you can see with sample size is now an option. And so we just have to fill out a few things in this menu when we're done. So really it's not too bad. So they wanted 90% confidence. Now target population. Here's the new thing for proportions. It says, assume we don't know anything. If you don't know anything, use 0.5. In other words, it's a coin toss. And then what's my width? Well, they wanted the width to be within 8 percentage points. Careful, that's 0.08. And so, whoops. Are they going to do it like that? That his estimate is within 8 percentage points of the true population proportion. It just doesn't seem right. There we go. I don't know why I didn't take it the first time, but I'm getting 423, and I might be right and I might be wrong because of one thing I got to make sure I'm reading correctly. They said they want his estimate within 8 percentage points of the true population. And actually, I think I am doubting myself here. I think I'm going to need to type in 0.16 instead. And so now I end up with actually a way better answer. I end up with 10, I think that was 106 or 107. Let me see. 106. And so let me talk to you about why I just doubled that really quickly. And I thought it was going to be double, but I wasn't sure. But let's just draw a quick picture, and I think we'll see why. What does it mean to be within 8 percentage points? It means if the true value was, let's just say 0.48, then if I move over 8 percentage points, then now I'm at 0.56, and guess what? That is within 8 from the total, but I could be within 8 from the other direction, and that should be, 0.08, but I think we get the idea is that if I'm within 8, then that's within 8 on either side, and so the width is actually double that statement there, and so it looks like I was right to double it at the end there, so be cautious of that. Up next, we have almost the same question, but this time, look at this. It says, what if you actually knew that it wasn't a coin toss about the percentage? What if you knew about 82% of people knew? And look at that, our sample size is now even smaller. We can go down as low as 63 people are needed, which is really interesting. So if you have some prior information, right, that can be really beneficial, because as long as it's better than a coin toss 50-50, you can get away with a smaller sample because of what you knew what was true at some point. Okay. At that point, there's some more questions to do here in 7.1, but we're going to move on now to 7.2, and we're going to show you that really we're almost done with this whole chapter. We just need to explore that other formula. We spent 7.1 doing the theory and learning our first formula. 7.2 goes by quicker because now we don't have to talk about the theory. We can just do a few examples and really be done. All right. So first, I just kind of want to highlight that, yes, that formula looks a little bit wacky, or this output looks a little wacky. But what I want to show is, hey, look, there's the x, there's the s of x, they're just writing the little sub x, there's the n, and they actually gave you the entire interval already there. So if they want me to write the interval, I actually already have it. It's just what's written there up top. So 85.74 and 91.76. Already done. It was given to me. The point estimate literally is the 88.75, right? As we wrote here again on this page, the point estimate is the first thing before the plus or minus, so x bar. And there it was right in the table. Lastly, they want to know what the margin of error is. Now this one is a little bit different because we haven't actually done this yet, but it's still an easy question, because we should know that the margin of error is how I go from my middle value to either of these ends. And so all I need to do is take my 91.76 and subtract my 88.75. Or, right, I could take my 88.75 and go to the lower value, the 85.74. And look at that, I get the same answer. So that must be my margin of error. How much did I move from my point estimate, either up or down? An even amount. I went 3.01. So really easy question there. No real math required. Okay, up next. And we wrote the note here that DF is n-1. So degrees of freedom is, honestly, it could be a whole collegiate lecture at the master's level, so we're really not going to dive into it. We're just going to say, hey, it's n-1, and it's used in the formula for reasons. Up next, they want you to find the critical t-value that corresponds to degrees of freedom 49 and 95% confidence. Now, there is a table here, and we can hopefully find degrees of freedom 49. If you don't find your value, you should always round it down, so we're going to be using 45. But now let's look up here. What am I going to use? They say area in 2 tails or area in 1 tail. Now, the other way of saying that is I want to be 95% confident, and that means that the collective area in the left little tail and the right little tail should be 5% left over. Or there should again be 2.5% in every tail. So let's see that. 2.5% in either tail or 5% in both tails collectively at degrees of freedom, let's see here, 45, because I should always round down. I get 2.014. 2.014. Which will just be 2.01. Great. And then, let's see here. Well, let's answer that degrees of freedom question. All right. And honestly, because, like I said, because there could be a whole lecture on it, I did some light Googling and just searched up what is degrees of freedom. And so it says the number of independent variables that can be estimated, or wait a minute, it also says the number of independent observations that are able to estimate. Let's see, there's another one that I like. The number of values in the final calculation of a statistic that are free to vary. And so when I read that last one, it says the number of sample values that can vary after certain restrictions have been imposed. That one seems like the best answer that fits, and it is. And really, again, it's just that is the definition, but what does that mean? Yeah, that's where we're going to not really answer that in this class. You could also, that'd be a good point to actually open up the textbook and just read it right from there. Okay, but the one other thing we need to do, though, is although we do have the degrees of freedom, simple calculation, just n minus 1, and we were able to use the table, of course, the question is, how do I do it in StatCrunch? And so let's see how we do it in StatCrunch. So if we go to Stat, and we go to T-Stats for, actually, let's see here, calculators, it's probably there, T-Table. And so if we have degrees of freedom 49, and we want the area between, right, to be 95%, there we see the 2.01 when it gets rounded. Notice that that's definitely a different value than what was in the table, but that's okay because it will actually still round at the same thing. So again, we just went to the T calculator. Notice that that was in stat calculators, not in T-stats yet, right? We'll use T-stats in a second, probably by this next question. But there we go. I'm going to skip over this one for the sake of time, and yeah, let's dive into going through a whole example. So first thing is they want, I gotta keep that StatCrunch window open. First thing is they want that T-stat. So I'm gonna go to the calculator, T, I want degrees of freedom, let's see here. There are 36 values, so 35 degrees of freedom. And I want the area between, or they want the area between, to be 95.95. And it looks like I'm going to be using 2.03. All right. Up next, what's the margin of error? And so, let me get my StatCrunch back. So at this point, I'm going to go to my T-Stats 1 sample with summary. And I've got some stuff to plug in here. I've got my sample mean of 3197.2. 3197.2. I've got my sample standard deviation of 692.6. I've got my sample size of 36. I'm doing a confidence interval with 95%, and I do want to see the critical value, and I compute. Okay, in order to get the margin of error, I need to multiply that standard error and my critical t-value. So let me do that just on my calculator here. 115.43 times 2.03. And I get 234.32, or 234.3 when I round to 1 decimal place. All right. Finally, what's the interval? And well, that was just there in the StatCrunch window. It's the 29, whoops. Oh gosh, but it's going to go away. Let me just move it off the page. I can see it, but I know you can't as I type it in. Or maybe I can just do that. All right, the 2962, let's see here, to 1 decimal place, 0.9. And then I've got the 3431.5. Great. And again, we can be 95% confident that the interval from the lower bound to the upper bound contains the true value. At that point, really, we've gone through just about everything we need to go through here by doing that one example. Well, there's one more example to do, actually. And notice I'm skipping over a lot here, but this one, just to show you, this one looks different. It has the raw data, so maybe I'll just show you this. We can open up this data in StatCrunch, and here's the idea. This time I can still say I want T-stats with 1 sample, but of course this time I say with the data instead of with the summary. I was doing a confidence interval. They wanted 99% confidence. Show the critical value. And I guess I can get rid of this old StatCrunch window. I've got this one now. And there we go. I've got my lower limit, my 0.185 when I round to 3 places, and my 1.287 when I round to 3 places. So already, that was super easy to do, and I had the raw data, so I still went to, again, where was that? I still went to t-stats, one sample, but instead of with summary and type in the standard deviation, mean, and whatever else, I just said with the actual data because I was able to copy it right from StatCrunch. The very last one, and this is the one technical note we need to be careful of, is this one is still the give me the sample size, and so t-stats, one sample with sample size. So we're back to using that menu. But there's one more thing we need to consider here that didn't show up before. So let me get to where I can see that menu. Okay, so let's see what they wanted. They want to be 90% confident, so 90. They said assume the standard deviation's 18. Sorry, but that's the thing. Sorry. Even though this would normally be a t-stat, just go ahead and use the z-stat. There are reasons for that, but it's essentially because they're telling you about the population standard deviation. You should actually use z instead of t, where you're using that everywhere else. Just when you're doing the tell me the sample size I should need, use a z value. I think the homework actually accepts the answer for both, but in traditional statistics, we use z when we're determining the size I need, since I don't know if it's too small or not. Also, it says within 5, and remember, we learned to double that. So, there we go. I wanted 90% confidence. I was told that I could trust using a standard deviation of 18, and the width is 10, and so my sample size is 36. Again, I think it works if you use the t-value either, or also rather, but there we go. Okay, so that's really it for Chapter 7, and you'll see the questions on the exam are very simple that come down to Chapter 7. StatCrunch the whole way through it. That's why we teach you the resource, and so I'll see you for Chapter 8.